So last we did balancing of equations. And it turns out that we don't balance equations just for their own sake. It's not just a fun game. We're actually balancing equations so that we can do this right here, stoichiometry. That's our purpose for balancing these equations, so that we can tell what our molar ratios between products, or between products and reactants, or between reactants even, is, so that we can make calculations based on how much material we're going to produce, or how much we should use, etc. Really please try to internalize this idea. A lot of general chemistry calculations we do, obviously they'll carry over into Gen Chem 2. This definitely does. But some of the more math-heavy stuff that we do is only useful in certain upper level courses, but not the case with stoichiometry. In fact, stoichiometry is one of the few calculation-heavy things that you'll even do in organic chemistry if you take that upper level course. Stoichiometry is everywhere, and I actually make the claim that it is the singularly most important concept in this course. So previously we just did balancing of equations. So looking at this equation, we might, we might put our elements here. We only have iron and sulfur involved, and they do have ones as coefficients to start with. When we total up, we only have one of each on this side. But over here we've got 2 irons and 3 sulfurs, right? So what we did before is we would modify the pieces that we needed in order to balance them. And then we end up with a balanced chemical equation. We're going to need that balanced chemical equation then to go to the next step. So when we balance equation, what we're really doing is we are finding the molar ratios for the different components, chemicals, let's say. That's a little bit of a slippery term here, but we are finding the molar ratios for the bits, the species involved in our reaction. So it is always a molar ratio when you balance an equation, not a grams ratio, not a volume ratio. If you're working with gases, it is always moles to mole, molar ratio. So there's our equation, balanced now. And so we can read this reaction to say, well, for every 2 moles of iron, this reaction needs 3 moles of sulfur to also react. And for every 2 moles of iron, 1 mole of iron 3 sulfide is produced. Or you could say for every 3 moles of sulfur, 1 mole of iron sulfide is produced. And those are coming directly from those coefficients we determine when we are balancing the equation. You could and should look at them as fractions to use in the dimensional analysis process. And so you can say, well, iron and sulfur, what do we have? Let's see. There's my iron. There are 2 of those, and there are 3 of the sulfurs. And that's how I would determine a ratio, molar ratio always, that I need for that. Iron and iron 3 sulfide the same way. And so you would see that there are always 2 moles for every 2 moles of iron for every 3 moles of sulfur. So you could set up this ratio, and what we'll do is we will, y'all know how fond of my parentheses and fractions I am, so we'll put parentheses around that, and we'll use it just like we used, say, grams per mole when we were trying to figure out moles or grams for a compound. Works the same way. It's a ratio, and it'll cancel out. So you could say there's 2. Back to the corner, we could say that there are 2 moles of iron for every 1 mole of iron sulfide. Works that way. And of course, you can invert these when you need to. So let's say you're given iron, trying to find sulfur. Well, you just flip this over, because remember that we're allowed to do this because they're equal in these. The numerator is equal to the denominator here. Well, it's still the case even if you flip it over. So how about a step-by-step process? What could we do here? We could use these ratios to convert between moles of one thing in our reaction to moles of another. So here's a new. Now this is different. This is a different equation. I just want to point out this is iron instead of sulfur. Now we've got oxygen reacting with our iron, and our balanced equation here is for two Fe2O3s. Now I do want you to keep the stuff we've done before, so you know that oxygen should be a -2, right? And there are 3 of them, so -6 total there. Must be +6, so divided by 2 units of iron. Therefore, this must be iron 3 oxide. You should still know how to do that. So a question might say, well, how many moles of iron 3 oxide can form from 6 moles of oxygen? So what am I given here? Let's see. So I'm given the 6 moles of oxygen to start with. And I guess I could look at it as if I'm given the balanced equation, although more likely for you, you'll be given an unbalanced equation. You'll have to actually balance it first. So we'll find this ratio, this molar ratio between the two. So we see that it should be 2 iron oxides for every 3 oxygens. So 3 moles. So I'm using my equality sign a little bit loosely here, but for the context of a stoichiometry problem, I can say that 3 moles of oxygen is equal to, for this given equation, 2 moles of iron 3 oxide. So we can use those as a denominator and numerator to cancel some things out. So then I'm going to use it that way, and so here's my starting 6.0 moles of oxygen, and so I just set it up like my fraction. And I literally cancel out moles of oxygen, leaving moles of Fe2O3. Now, you will see me probably shortcut this a little bit, and I will just put 2 Fe2O3s over 3 O2s and just cancel out the species, the O2 part. The way this is written here in blue is probably technically better, but I'll be honest with you, I'm probably going to be lazy and leave the moles and moles off. Just if you do leave it off of one of them, leave it off the other so that the dimensional analysis is correct. But if you do that, it's still a true statement to say, for given this equation, the formula unit ratio, there are actually 2 iron 2 Fe2O3 formula units for every 3 molecules of oxygen. It's still technically correct. So you can still just cancel out the O2s. Just warning you that I won't always put the moles in here like in blue. But you would still, either way, you would still get the same units out at the end. You get moles of target compound, which is what we were after in this case. So what can we do with this? So we're combining this mole factor with conversions, and a lot of times you'll see be given in grams to start with of one or both components or several components, and you have to decide what your mass coming out the far end is or something like that. And so we can do that with this process, but we might have to staple a couple of processes on the beginning or the end to do that. So you could take grams of something in a reaction and go all the way to grams of something else in the reaction. So let's say we have mass of species, and species here, I've been using it a little bit, so I hope that you've heard the term and you might have wondered what I mean here. The reason I'm using this is, like in that last slide when I said iron 3 oxide, we might say a molecule of iron 3 oxide, but technically that is not correct. Should be a formula unit because it's an ionically bonded compound. Well, so then we got to try to always keep up with which ones are ionic, call them formula units. That confuses people because we're not calling them molecules like we'd call one H2O a water molecule, and that would be correct. But So if I just say species, I'm just talking about things in the reaction. So my iron oxide could be a species. You could have water as a species, oxygen, whatever, the components of the equation. So the mass of species A, and I would like to get to the mass of species B, some other species that is participating in this reaction, right? So please, please, please be very, very careful about this. It always gets people. Because you would like to just say, well, look, I've got ratios, so I could just go from the mass of A to B. That would be absolutely incorrect. You cannot go mass to mass using stoichiometry. What you have to do is you have to turn your starting mass into moles. Then you affirmative can go moles of one thing to another in the equation because these are molar relationships in the balanced equation. Now once you have gone from mass to moles and then you can go moles to moles, now you can take your new moles of B and convert back to a mass, but you cannot go directly from grams to grams. So we're going to do a couple of major things with this. One is going to be we're going to determine limiting reactants from it. I'm going to walk through a couple of examples of that. And then we're also going to do another thing in a bit called yield, which is closely related. Okay, so let's see how this limiting reactant idea works. So let's take, here's that copper reaction that we had, the copper nitrate that we had before. And so we'll take it and we'll look at what's going to happen with limiting reactants. Now my question is phrased as, what if I had 100 units, and by that I mean formula units, molecules, however you want to call them. Formula units is actually more correct in this case because these are ionically bonded. So if I had 100 units, 100 of each of these, how much product can I make? Now let's focus on the copper hydroxide product. So if I have 100 units of each of these, it might be tempting to say, well, probably get 100 units of products, but we won't. So here's our copper nitrate, and here's our sodium hydroxide, right? And we're going to make copper hydroxide and sodium nitrate. But remember, when we did this originally, it's not balanced when you do this, and so you have to add some things in here. This 2 and this 2, and I'm gonna go ahead and do what I've been asking y'all to do. Specify the 1s here also, right? So we've got to add those in to balance the equations, right? So for every one of these, it's going to take 2 of these, and one of those is going to produce 2 of these are going to be produced, right? So that should make a little sense, right? Well, now, if I have 100 of these to use, 100 of these, and I have 100 of these to use, I'm using up 1 of these at a time, but I'm using up 2 of these at a time. So I'm going to say that, look, even though I've got 100 units of the sodium hydroxide, I only get to do 50 cycles of the reaction because each cycle is going to use 2 sodium hydroxides. So they run out 2 at a time. So I have 100. I use 2 of them for the first cycle of 98. 2 more, I've got 96. So you only get 50 cycles until you have run out and you have 0 sodium hydroxides left, right? Now, if you had 1 extra sodium hydroxide, right? It can't react here. There's no more place to put it. So it's just going to kind of hang out on the other side. Okay, we're going to walk through one here with numbers instead of little figures on it. So here in this problem, I've got 75 grams of silicon. first. Now I've already balanced. I'm sorry, I should have pointed that out. I've already balanced the equation here, 3, 2, 1. So if we've got 75 grams of silicon to start with, right? Now remember, we can't just do anything with it as grams, right? We've got to take 75 grams, and let's see. If I look up the molar mass of silicon on the table, I get that it's about 28 grams for 1 mole. And should have done this to start with, but I'm going to go ahead and not rewind and redo it. I'm going to stick it in here, maybe so that it sticks out in your head. I've got 75 grams that I should put of silicon specifically, and then 1 mole per 28 grams. And that's going to give me, what do I get here? 2 dot, I got 5, 6 here. I only use 2 6 on my molar mass, though, so I'm going to go with, well, I'm going to go back and recalculate it later, and I'm going to keep my 5 6 for now. So 2 dot 6 7 8 6 moles of Si. Now let's look at what I've marked out here. I cancel out just the grams part, leaving silica and moles. So I have 2.678 grams of silicon. Right? Well, I can take from my molar masses above, I'll be able to do something with that. Let's see what that'll do for me. If I take, I want to know how many moles of Si3N4 are going to come from my 75 grams of silicon. Well, I've already changed it into moles, have to do that. So now I just need silica to cancel out as a species here, and instead end up with Si3N4. The only way you can do that is canceling out whole species. I've got silicon as a species, and I've got silicon nitride as a species, so I can put them here. And I know the molar ratios, you know, a 1 and a 3, so I know that my expected is 0.892586. What are my units here? Erase this and move it over here, because my units now are, well, let's see, this cancel this, leaving moles of silicon nitride. Okay, so I've calculated the moles of silicon nitride. However, we don't know if it's the right one yet, so we have to go do the other one also. This one's a little easier because it starts as moles. We would have to get it into moles if it weren't, but this one starts as, so we can just skip step 1 and say 2.000, should be a decimal here, moles into, right? We'll do the same process again. I'm going to go back to blue so you see that I'm getting it from the same place. Cancel out my N2s. Gonna leave silicon nitrides. It's really hard to write with this mouse. It's actually not even a mouse, it's a trackball. N4. Now let's see, numbers that go with that. Still the 1 here, but this time there's a 2. So one of these for every 2 of these, right? And I hope you see quickly math-wise that that's going to be 1.000 moles of N2. Now, for the for the really easy part, what you do is you say, well, let's see. This value says it produces less, a more limited amount. Therefore, this one is the true value that I expect to be produced, and my silicon ends up as my limiting reactant. So the other thing we're going to do with very, very almost identical calculation, we're just going to call it something different at the end, is yield calculations. Okay, there's one small bit of extra. So yield is an idea of what are you getting out of, what is the equation yielding? What is it producing? How much stuff? And we'll need to talk about three different kinds at least. We'll talk about an actual yield, a theoretical yield, and a percent yield. Okay, so our theoretical yield is what we just calculated from theory, from the numbers and from the stoichiometry. It's what we calculate. So you could also call this a calculated yield, but most often it's referred to as a theoretical yield. So it's the amount that you are predicting from the numbers how much it's going to have. You calculate it using that balance equation just like we did, and you do have to include figuring out which reactant is limiting. It could be more than 2, just so that you know that the lesser amount is the one that you're going to be predicting as your theoretical yield. Okay, now your actual yield, that one you actually put it on a scale and measure it, or you measure it some other way. A lot of times we'll do it with spectrophotometry or something like that. But you measure the amount actually obtained in the experiment. And then, of course, your percent yield is pretty simple to calculate. You just take your actual, how much you actually weighed out at the end of product, and divide by your theoretical or predicted yield, and then multiply by 100%, and you get your percent yield. Okay, so the way we do predicted or theoretical yield is, here's our equation from before, and you just do all that stuff that we did last time, and then you say, hey, look right here. This limited, my silicon was my limiting reactant, and I had to predict how much stuff it would produce in order to determine that. Well, in the process, I determined this lower amount, the smaller of the two amounts, is your theoretical yield. So I've already calculated my theoretical yield. It is the lesser yield of the two possible ones, or it could be more than 2, that we predicted from our reactants to determine limiting reactant. So the limiting reactant produces the theoretical yield.